Alright, 3.6, making connections. How can you tell if an equation is a growth or decay? And from an equation, you have not a table of values or a graph. We have to be able to tell if it's a growth or decay, so that we can get a picture of an idea of the actual graph itself, so a picture of the graph itself, especially when we're sketching graphs. So, first thing we look at is we look at the base. If that base in that exponential function is greater than 1, the graph starts, that's right, starts as a growth. And what do I mean by that? You'll see in a minute. Now, if the base is between 0 and 1, then we say that the graph starts off as a decay. So, if it starts off as a growth, the base is greater than 1, you should suspect that your graph is going to look something like this. And if it starts as a decay, you should suspect that your graph is going to look something like this. Now, knowing that, we then look and see if there is any, that's right, reflections. What happens is when there's a reflection, okay, what we have to do then is when we look at the reflections, we have to see if there is one reflection, so either a vertical or horizontal reflection. And if there is only one reflection, then whether it's a growth or decay, it turns into the opposite type of graph. So just to give you a quick example, if it was a growth, it started off as a growth, and it was a horizontal reflection, the graph may look something like the following. And if that is the case, then that turns into a decay. If the original growth had a vertical reflection, the graph would turn into something like this. And that turns into a decay as well. And the same thing is as if it was a decay. If it was a decay and had a vertical reflection, a horizontal reflection, it would look like this. So it would turn itself into a growth. And if it had a vertical reflection, the graph would look something like this. And that would mean that it would turn itself into a growth. So the idea is if there is one reflection, it will turn into the opposite type of, whether it's a growth, it will turn into a decay. If it's a decay, it turns into a growth. Now, if there's two reflections, so a horizontal and a vertical reflection, then the function will stay the same. So for example, if we looked at original growth and reflected twice, the graph would look something like this. And that means that if it looked something like that, then that would be a growth. And if it was a decay originally from the base, well, once we reflect it twice, it would end up looking something like this. And that, folks, is also a decay. So you would have a decay. So again, you have to be able to look at the equation and have an idea what the sketch would look like. All right, now, a couple of other things that's important. Doubling is considered a growth. So if you double something, okay, so let me explain this function to you. In science, they like to use A0 to say the beginning. Doubling, the base is 2 always, and then the equation will have these two here. Now let's talk about this bottom, the denominator of the exponent, and the beginning number will always have numbers there. There will not be just letters. This one up here represents the time that has elapsed, and that's the same t here, and that would be considered your variable t. Now A0, it means, or just A, means that it is the original amount that you started with. Okay, now when you have that starting value, then it's doubled, so that's what the 2 stands for, is the doubled. And doubled represents you start with 100% and you add another 100%, which equals 200%. Over here, there's a lot there, so let's just process this information slowly. So the total amount of time elapsed is up here. T is a variable. That is the number that the question might ask, say how much how much product do you have after a certain amount of time. D stands for the doubling period. So how long does it take for the actual product to double? Okay. And then finally, this A at T stands for the amount after T time. That is like your Y value. All right. Now, half-life is considered a decay. And half-life is, again, you have the same as the last one, but here we have a half as the base. So there is the half-life. A, again, stands for the original amount. It's the starting value. Half is the half-life, 100%. You start with minus 50% is equal to 50%, which is 0.5. So what that means is if you have half the amount of product left, it would be 50% of the product, or half. T represents the time that's elapsed over a certain amount of time, and H represents the amount of time that it takes for the half of the product to exist. And again, the last one, A at T, is the amount after T time. So these are all the explanations of each piece of the equation. Example 1. The population of Canada in 1981 was approximately 24 million people. The population since then has increased 1.4% per year. Determine an equation that represents this data. So, let's bring out an equation. P at T is equal to 24. 24 is the starting number. I know it's million, folks. You can write all 6 zeros, or you could represent the P is in the population of millions. P at T is in millions. Now, this part over here, 1 plus 1.4%. 1.4% is converted to 0.014. You start with 100% and you add 1.4%. So let's talk about the word percent and how do you convert a percent to a decimal. Now you should remember this. Per, folks, stands for out of. Out of mathematically means divide. Cent, if you remember in French, means 100. So basically percent is out of 100. So we took the 1.4 and divided by 100 to get this value. 1 plus 0.014 to power of T over 1. Takes 1 year to grow that amount. T is the time over however many times that they need it for. Now, very important to note, the population is obviously in millions because it wasn't 24 people but 24 million. And T, what else is important, is the time in years since 1981. So it's important that you have this up here as T, or if you want to know times in years since 1981, you would do T minus 1981. You could do that as the exponent. On the bottom, it has to be a 1. When you simplify it, you get P at T is equal to 24 times 1.014 to the power of T. That's simplified. All right, moving forwards. Same question that we have, but it's a part B. And there's the equation. What should be the population of Canada in 2016? Let's find out. Well, T will have to be 2016 minus 1981, and that equals 35. So it's been 35 years since this formula was calculated. That means that P at 35 is equal to 24 times 1.014 to the power of 35. Very important, P at 35, this is like your Y equals. We don't touch this, we don't separate it. This 35 is not separatable. You cannot separate this. This is Y. This is like Y equals. And you end up with 39.042684. Now you might be wondering, how come I chose so many decimals? Well, remember, P originally is in millions. So we need to have at least 6. We need to have 6 decimal places to have a number that is more accurate in terms of number of population. So the population should be 39,042,684 people. All right, next part. P at T is equal to, there's the formula again, and C asks, when will the population double? Well, folks, the easiest way to do this is use something that we're going to be learning in grade 12 called logarithm. And I know that a lot of times you're taught these in other courses and not really told what it is. In grade 12, you will learn about this, but in the meantime, we're going to do the fast way to get this answer. Set up the equation. So we need the population to double. So that's where that came from. This 48 is 24 times 2. The original population is 24 times 1.014 to the power of t. Now, what we have to do is we need to look at this and see what we need to do first. That is, divide by 24. We get 2 is equal to 1.014 to the power of t. Now, if you think about it, we could have started off with this equation, because if we started with 100%, we need to get to 200%, it could be this way. But if you don't understand that, folks, this is perfectly fine. All right, now we want to get rid of the t. To get rid of t, we have to take the log of the answer divided by log of the base. And we use the log button in your calculator to calculate the value, the answer in the base. So the t is equal to 49.8563. So now we're using 50 years, folks. How come we're using 50? Not only does this round to 50, but if we had chosen 49, in year 49 the population doesn't double. It is near the end of 49, so that by year 50 the population will have doubled. You can't do part of the year in this case because it asks per year. And so in 2031, the population should double. Now, I could change the question and ask how many months. And you would have to calculate how many years and months will it take for the population to double. So calculate to the nearest month. And you would have to find out how much this decimal would represent in terms of months. All right, folks, that's the end of the lesson. Here is your homework. Have a numerical day. Take care.